So this tutorial is going to be on optimizing the layer thicknesses of an organic photovoltaic device. I've done a tutorial previously on optimizing the layer structures of a perovskite solar cell, but this one's going to be on an organic device. Now, in this tutorial, we're only going to look at optimizing the layer thicknesses for optical performance. We're going to neglect electrical performance. And it's quite useful to do this because it gives you an idea of the sort of the maximum ideal structure of your solar cell if you don't consider electrical effects. And it sort of gives you an idea of how far your device is, if you're designing a device, is from being optimum from the optical perspective. Now, the wonderful thing about just doing optical simulations is it's very easy to get the refractive indices, so the N and K data, for your layers, and that's all you need. You don't need to worry about mobilities or anything like that, and it just gives you a very good insight into device performance. So this device has got 1, 2, 3, 4, 5 different layers. So this simulation comes from new simulation and scripting and fitting, and it's just this one here, which is optical layer optimizer PM6Y6. So if you look in automation under parameter scan, there's this this scan already set up for you. So if you open this, you'll see that we've got 2 layers put in here already. So I'll just put this on top and get the layer editor back up. Where is it? There it is. So we're going to be changing the thickness of epitaxy PM6Y6, which is that layer there, and the dy of the object, so the thickness, and we're also going to be changing the dy, so the thickness of ZNO, which is that one there. So what I'm going to do is add another layer to this. So I'm going to say let's also change the thickness of the say the ITO. Let's change things to the ITO. So put in a new row with the plus button, select it, click on the dots, and then we go to epitaxy, ITO, and then dy of the object. Okay, and that'll appear there. And then I'm just going to copy this. And I'm going to say that we're going to go from 10 nanometers to 40 nanometers. How thick is this? Oh, it's 100 nanometers. Let's go from 100 nanometers to 150 nanometers. Let's take that to 90 actually, no, 80. And put that down a bit to 120. We're going to go in steps of 10. So this is the start value, the stop value, and the step. Clearly, the smaller the step, the longer the simulation will take. So, I could have put this at 0.1 nanometers, but that will take a bit longer. And you can also add as many layers in here as you want. Key to notice is that this fast optimizer button is depressed. So when it's not depressed like this, it will save the results of all of these simulations in the output. So it'll save like all the JV curves, all the charge density curves, all the sort of the fluctuation of LUMO and HOMO as a function of voltage, everything. But when you're optimizing a device, you're not really interested in that. So when you click this on, it's just going to save the figures of merit of the device in a big table. So it won't save the actual simulations. That's much, much faster. So I'm going to click Run Scan there, and just get rid of that. And what's happening is you get this window popping up here, and you see that that's the progress simulation. And these are all the individual simulations being done. And what we get up in the end, so I'm now going to, on a screen that you can't see, I'm going to navigate to Home Rod Desktop Test 3. So I'm just going to do that. Open that. And you can do this in Windows Explorer or whatever if you on Windows PC. And it's put in that simulation directory as a directory called Optimize. And in there we've got optimize output.csv. So I'm going to double click on that. And it's going to open it in LibreOffice, but you could open it in Excel or whatever you want. And here, what we've got is the first 3 columns of variables we're changing. So it's thickness of layer of 2, 1, 0, and notice the layers start at 0. So, oops. Something weird has happened. There we go. So this is the layer editor. So layer 0 is that layer, layer 1 that layer 2 that layer, layer 3, layer 4, and you put if you had 4 or 5 different parameters you were changing, they would appear in the columns here. Then we've got light fraction photo generation here for layer 0, layer 1, layer 2, layer 3 and layer 4. And what this is the fraction of light that's absorbed in that layer. And this second column here, so layer 0J, layer 1J, layer 2J, layer 3J, layer 4J, that's the maximum photocurrent that layer could possibly reproduce if all the absorbed photons that get absorbed in that layer could generate charge. Now, clearly in the active layer, which I think is, let me just, which is the active layer is layer 0, 1, 2. So if we look at the active layer, there's the active layer. The current generators here could actually potentially reach the contacts, and we could do useful work with that current. But clearly, any sort of photocurrent generated in, say, the ITO or the metallic back contact here, that couldn't do useful work. So this would be so this column here would be wasted current. So this column here, this is the only one that actually do useful work. Now what we can do is we can sort these columns by the, so if we sort it like that, and then we click on this one and we say sort descending, this is then this sorted and descending photocurrent that's generated from that layer, and we can look on the left, so we follow this along, look on the left, we find out what the optimum layer structure is for our solar cell that produces that particular current. So it's this. So there we know that layer structure there is the optimum for this device. So I think that's quite useful. I'll just show you one or two more features whilst we're here. So we're just doing optical simulations here. So optical simulations are governed by this optical mesh. Now, Y is a number of mesh points in the, so how the simulation is. So let me show you let me step back. The simulations that performed on this device were transfer matrix simulations. So if we open the transfer matrix window and click yes, this device, we've actually been exciting this device with I didn't realise this, I thought we were exciting with AM1.5, but we've actually been exciting this device with a laser. So there's actually a 500 nanometer laser. So the optimization we've just done is for laser excitation, which I guess is quite cool in itself. And you can see the laser sort of streaking in here. Now, this is sort of this is position within the device. So 0 is at the top and 350 is at the bottom, and this is wavelength. And you can set up this this mesh, this computational mesh, using, I'll just keep that on top, using this mesh editor here from the optical mesh window. Now we've got 150 points in wavelength, but you could probably reduce that. So you could probably reduce that to say 50 potentially. We could also probably reduce the number of points in position space to half, say 100. So if we rerun that, it looks a bit blocky, but that's probably good enough for your computation, especially if you're using a wider light source like AM1.5. So if we set AM1.5 there and rerun that, you know, that's probably that sort of this optical mesh is probably good enough for this computation. So if we rerun that optimization now, where's the optimization? Where's it gone? There we go. If we rerun that, it's probably going to be slightly faster in running, because we've reduced the number of mesh points. And then we could go back and look at that CSV file again and re-optimize and sort of pick out which device structure is best for our AM1.5 spectra we've now put in it. So should we do that? Yeah, we'll do that. We'll see if the structure's changed. So here's our CSV file again. So this is now optimized for the AM1.5 structure, and sort this layer, sort descending. Sorry, yes, there we go. So if we're looking across, it reckons that this is the optimum structure for that particular device. So I hope you found it useful, and any questions, shoot me an email and I'll happily respond. So yeah, thank you very much for watching.